Hello everyone, welcome back to the course on measurement and instrumentation, and this is the 8th lecture of our second module where we are discussing different topics on analog meters. In today's class we will be talking about analog meters which is used to measure current. Basically this is known as ammeters. However, we will see that how these ammeters are in general designed and how to connect them in a circuit, and we will see certain basic ideas about this ammeter. Of course, the basic construction and increment of its range and other things we will see when we will actually talk about the actual analog meters like PMMC and moving iron type of instrument. But before we actually jump into the ammeters, let us quickly see the basic construction of a electromechanical indicating tools, because all these ammeters, voltmeters or whatever we talk is actually this electromechanical indicating instrument, because we are discussing these analog meters. Okay. So, the basic idea is the electromechanical indicating instrument are the devices which converts electrical input. The input is mostly in the form of current or voltage into certain mechanical motion, particularly the rotational motion or say deflection that we have understood of a pointer over a calibrated scale. The calibrated scale of course has not to be always linear. Depending on the instrument, we have linear as well as non-linear kind of scale. Okay. So, irrespective of the specific type, be it PMMC or a dynamometer or moving iron, their construction have similar systems. Basic functionality remain similar. Okay. So, the construction of electromechanical indicating tools has three main systems in it. The first is moving system. Sometimes it is confused with deflecting systems or indicating systems, but they are all actually defined separately, but in this course we are seeing them together. Okay. So, in the moving system itself we will see deflecting system, indicating system and the support system for this moving systems. Okay. And the second thing is the controlling system, and third is the damping system. Please recall that similarly we have seen three different torques, where we have seen the deflecting torque, we have seen the controlling torque as well as the damping torque. Those torques has to be generated, or those torques are basically generated by these three different systems. Okay. The deflecting system, the controlling system and the damping system. Okay. So, however, we are not calling it in this part of the analog meter course deflecting system, we are calling it moving system, because we are more interested in seeing its construction rather than we are seeing it from a torque point of view. Okay. So, that is why I am calling it a moving system, but it is all up to you. You can think it as three different system or six different system, where the deflecting system, indicating system and supporting system makes different part. Okay. But in this course we are talking like as three different systems. Okay. Let us see what is a deflecting system. Okay. We have already seen this during the discussion on our torque. Okay. So, the deflecting system, as the name suggests, produces deflecting torque when the measurand is applied. The measurand is in the form of certain electrical parameter, be it current or voltage. Okay. The torque is generated due to the electromagnetic induction, or if there is any other way, we will talk about that. Okay. The common implementation is like is done by say moving coil in a magnetic field, or say a movement of a soft iron piece which is magnetized by a current carrying coil in case of the moving iron tools, as well as the interaction of two current carrying coils in the electrodynamometers. Okay. The moving system include all parts that move under the action of this torque. Okay. This include say the moving coil or the iron piece that we have just seen. Okay. The spindle as well as the pointer. Okay. And they are designed to be lightweight so that the inertia is minimized as well as the response improved. Okay. The improved response is the result of the lightweight of the system. Okay. So, the moving part, as I have mentioned, should be light, and the frictional force should be as low as possible, and ideally it has to be 0. Okay. So these two requirements should be fulfilled so that the power required by the instrument for its operation is as small as possible. Okay. Then we have a supporting system or the supporting system for the moving element. Okay. So the deflecting force or the torque in an electrical measuring instrument is kept very small. Okay, so that the instrument consume as small power as possible. Okay. So this small power also ensure that inserting the instrument into external circuit do not cause any disturbance into the actual circuit. So they are designed in such a way that when you connect it into external circuit, because ultimately the aim of all these instruments is to measure say flowing current or dropped potential across certain resistance or in a resistance value or say a certain impedance value. Okay. So the idea is to keep this as small as possible to ensure that when you connect it in a circuit in series or parallel, irrespective of that, the disturbance caused is minimal to the original condition of the circuit. Okay. To ensure smooth frictionless motion and longer life, therefore mechanical support is required for the moving system, and the moving system itself is not sufficient. Okay. So different kind of support mechanisms are employed based on how sensitive the instrument is and what conditions it will face while it will operate. Okay. So in general, the support system can be grouped into three different categories. The first is the suspension system. Second is the pivot and jewel bearing system. So suspension system and the pivot and jewel bearing system actually are kind of complementary to each other, and then we have altogether different kind of suspension system which is known as taut suspension system, or sometimes it is also known as taut band suspension system. Okay. So because we have two different bands to support this moving system, so this taut suspension system is sometimes also known as taut band suspension system. Okay. So let us quickly see that what is this suspension system and how taut band or taut suspension system is different, and how they can actually support the moving system of an electromechanical indicating tool. All right. So if I talk about a suspension system, it consists of a fine ribbon shaped metal filament for the upper suspension and a coil of fine wire for the lower part, as you can also see in the figure. Okay. The ribbons are usually made up of spring material, which is usually made up of beryllium copper or phosphor bronze. All right. The lower section of the suspension is coiled to minimize the mechanical resistance. This also ensure that the moving system experience almost no restraining force. However, this can only be minimized, but it cannot be zeroed down. All right. Therefore, if you see, we have another kind of suspension system which is taut suspension system. Okay. So suspension type of instrument can only be used in vertical position, and that too when this moving coil or moving part is balanced. Okay. So they can only be used in such a case that when you have this upper and lower suspensions and the moving part is balanced on top of it. Okay. So they can only be used when aligned in a vertical kind of position. Okay. However, a taut suspension system uses a flat ribbon type suspension which is positioned above and below the moving element, something like this. Okay. So if you remember, what we have seen is in this case of suspension system, this was having a fine ribbon shaped metal filament for the upper suspension, while the coil of fine wire of in the lower part we have coil of fine wire. Okay. However, in this taut suspension you have a different kind of arrangement. You have a ribbon type suspension which is positioned on at the top as well as in the bottom. Okay. and these ribbons elements are actually held tightly to maintain stability and alignment of the moving part, making the system more stable and avoid any kind of balancing situation or balancing requirement which was posed by a simple suspension system. Okay. So, in this case a spring mechanism applies continuous tension which ensures the suspension stay properly stretched and responsive even in the case of unbalanced conditions. Okay. So, you can see these springs which are actually providing the tension which is required in the taut suspension kind of system. In the suspension system, usually this you have a pivot and jewel bearing kind of system. Okay. The moving system is mounted on a spindle, which is this kind of spindle is there, which is mounted on a, this spindle is made up of hardened steel, and the two ends of the spindle are made conical and they are polished, like you can see this, okay, to form a kind of pivot. Okay. This pivot is very important for the movement of the system, and they can move in this jewel groove. Okay. So, these ends fit conical holes in the jewel. We are calling it jewel because they are kind of sapphire, which is artificial jewelry basically. Okay. So, these are made up of sapphire. Okay. Sometime even the older generation of these instruments were having ruby also. Okay. So, these ends fit conical holes in jewel located in the fixed part of the instrument, and these jewels, which are preferably made up of sapphire, forms the bearing, and that is why the name is jewel bearing. Okay. So, this kind of system also, if you see this motion, okay, it also provides certain kind of friction, maybe very less, but there is certain kind of friction. So, if you see among all these support system, you have the taut suspension system as the most advanced kind of suspension system. Okay, and they are actually used in all the high end instruments. Okay. So, this is a bit about the moving system and deflecting system. Along with this, you have indicating system, which comprises pointer, which is nothing but a kind of metallic needle. Okay, and then you have a calibrated scale. This calibrated scale is very important, and it varies based on what kind of instrument it is. Okay, and it converts the mechanical deflection into a readable indication. Okay, the scale may be uniform depending on the tool, as I have mentioned, depending on the deflection. If say deflection is directly proportional to the quantity that it measures, say it is directly proportional to say current. Okay, or say if the deflection is directly proportional to, in place of this I, it is proportional to I square. Okay. In these two conditions, the scale will vary. In the first condition, I am calling this case 1, okay, and I am calling this case 2. All right. In case of case 1, the scale will be uniform and mostly utilized in say PMMC kind of tool, which we are going to of course discuss after this week. Okay. And then you have this non-uniform kind of scale, okay, which is kind of possible in this kind of condition where theta is directly proportional to I square or so. Okay, and this is more relevant to instrument like say moving iron or say other kind of instrument where this deflection is directly proportional to I square in place of I. All right. Then you have controlling system. Now, this system restrains the motion of the pointer and ensure it comes to steady position, which is proportional to the measured quantity. Okay. We have discussed about this controlling system a little detail when we talked about the controlling torque. Okay. So, we have seen that this controlling system provides a restoring torque which balances the deflecting torque which is produced by the moving system, okay, or the deflecting system. Okay. Then we have also seen a damping system or damping torque earlier, so which was produced by the damping system. Okay, and the damping system ensure the pointer settles quickly without any kind of further oscillation at the end point. Okay. So, it prevents the pointer from even overshooting the correct value, and it makes it go to say both the ends of say extreme of this pointer, okay, without any kind of oscillation. And we have seen number of damping system which like air friction damping, if the friction is provided by air, okay, the piston kind of arrangement we have seen, okay. Similarly, it can be due to fluid friction, it can be due to say eddy current and so on, okay. So these are all the damping systems. Irrespective of what kind of electromechanical indicating instrument it is, be it PMMC tool or be it moving iron instrument or be it electrodynamometer, okay, the basic constituent including the moving system, the damping system or indicating system remain similar, okay, if not same, fine. So we will be taking all of these analog instrument in more detail in the next week's lecture, okay. However, all these instruments will be utilized for certain measurement, be it current measurement or be it voltage measurement or say determination of power or energy. So let us try to understand these meters before we actually see these analog instrument in more detail, okay. And first and very important meter in this discussion is the current measuring tools, or we call it ammeters, okay. So ammeter is an instrument which is used to measure electrical current in circuit. This is as simple as this, but there are certain rules and regulations that how these ammeters will be connected in the circuit or through the resistance through which you want to measure the current, okay. So these ammeters are always connected in series with the circuit or the resistance through which you want to measure the current, okay. This is very much important to note, okay, this connection in series. Otherwise, if you connect it in any other fashion, you may read some inaccurate result, and let us try to understand this with one example, okay. Say I have very basic circuit, okay. Say I have these resistances, fine. Say this is known voltage source or a battery source, say V, okay. This is resistance R1, this is R2, R3 and say R4, okay. I want to measure current I1 which is flowing through this resistance R2. There are number of ways by which you can measure this current mathematically. You have say there are certain known laws, you are already aware of them because you might have definitely studied it in the network theory or in the circuit theory course, that you have Kirchhoff's current laws, voltage laws, then Thevenin's theorem, Norton's theorem, etc. Using all those you can calculate this current, right. However, for practical measurement, what I have to do is I have to connect a meter in series with resistance R2, okay. For that kind of connection, what I have to do basically is I have to first disconnect this R2 from this point, okay. So I have to disconnect it and reconnect it with the meter which is my ammeter, right. So this is how ammeter will be connected with the resistance through which I want to measure the current, okay. If you say this is, I am calling this ammeter A1, right. Say if you connect this A1 say at this point, or there is say another ammeter A2 at this particular point, okay, or say there is another ammeter here which I am calling it say A3, and say there is one more ammeter, this is A4, okay. So you have this A1, A2, A3 and A4 in place, okay. Current you can measure through all these ammeters, okay. However, the current which is flowing through this R2 which is I1 will be reflected by this ammeter A1 correctly, fine. So an ideal ammeter has zero resistance, because if it has a finite resistance, it will definitely interfere with the current which is flowing and the measurement will not be accurate, okay. If it is 0, it will not affect the circuit current, or if it is said otherwise, if it is not 0 means it will definitely affect the overall circuit current, okay. However, A real ammeter has a small but a certain finite resistance. It cannot be 0. Okay. This small resistance even can cause a slight voltage drop in the circuit, and a small measurement error will happen compared to the ideal case. Now, let us come back to this particular example that we are seeing. Okay. Now, I have resistance R1, R2, R3 and R4 in place, and now say this ammeter. So now for the time being I am disconnecting all these ammeters and only ammeter A1 is in place, right. Now, since this is a real ammeter or not an ideal one, okay, it will have certain resistance. Okay. Now, let us call the resistance of this ammeter as say R5. Okay. Now, if you see this circuit, in place of this resistance R2, okay, now I have a resistance R2 in series with the resistance R5, which is very small. Okay, because this is resistance of the ammeter A1. Okay. So, earlier say if the voltage drop was say V1 across this R2, okay, or let us draw it separately. So, this is R2 and the voltage drop was say V1, okay, because of this battery V across this resistance R2, okay, and the current flowing through this was say V1 by R2. Now, the current value will be V1 by R2 plus R5, right. So, the overall resistance of this branch has increased, maybe not that significantly, but it has increased. Okay, because of which the current will drop. All right. So, the current value is decreasing when you are connecting certain ammeter, means it is directly influencing the parameters of the circuit. Okay. When current flows through the moving coil, it interacts with the magnetic field of the permanent magnet, if you see its construction, okay, and experience a force. This force is the Lorentz force. Okay. And this force basically produces a mechanical torque on the coil which is moving, and this will cause it to rotate and move the pointer over the scale for the measurement, and that is how a basic fundamental ammeter works. But this is very specific to certain kind of tool, but it may vary. Okay, what we are discussing right now may be for a linear scale kind of device, but there can be devices which are non-linear. So, just I wanted to tell you that how this ammeter basically works using this analog meters that we have seen. So, when you try to measure certain current, okay, through coil which is called a moving coil that we have already seen, okay, this current will definitely interact with the magnetic field because this moving coil is placed inside a permanent magnetic field, which you have seen that a U-shaped magnet, for example, in the PMMC tool is in place. Okay, and since this current is flowing through this coil, of course, this will experience a force, and this force actually produces a mechanical torque on the coil. Okay, this is basically the reason behind the rotation of the pointer over the scale which you want to measure. Okay. This, as I have mentioned, is a maybe example of a linear device. So, ammeter for this kind of, based on this kind of principle, are usually linear in nature and have a uniform scale, okay, where equal increments of current produces equal spacing on the scale. However, it is just one example. Please note there can be ammeters which has a non-linear scale as well. Okay. In this ammeter, this what I have talked about is the moving system, because we have seen that all this kind of instrument has moving system. Then you have other systems also in place, like control system, then like damping system, etc. Okay. In the moving system, the deflecting torques basically turns the coil from its zero position, while the controlling spring now comes into picture and oppose the motion of this pointer by providing a restoring torque through its spring constant. Okay. The pointer now settles when these two torques are equal in magnitude but opposite in direction. Okay. So, at that point where this controlling torque, this tau c is equal to say deflecting torque, okay, this is the steady state position when they will be equal, and now it will try to come back to its original position. Okay. So, the essential requirement for connection of a ammeter is the instrument should have low internal resistance, so that its insertion in a circuit or in an external circuit will not change the current or voltage which is already existing in the circuit condition. Okay. It should consume minimal power to ensure accurate measurement without any energy loss. Okay. So, this is a typical example on how a ammeter is connected in a circuit. Okay. The ammeter in this case, for example, is connected in series, so that the same current I which is flowing through this resistance is also flowing through this ammeter. Okay. And this will ensure accurate reading of the current I. This current is unknown, which we want to measure, which is flowing through this load resistance RL. Okay. The power loss in an ammeter is usually denoted as I square RA, where I is the current to be measured and RA is the resistance of the ammeter, which is, as we have discussed, is very small. Okay. The ammeter should have a low electrical resistance, so that they cause a small voltage drop and basically do not consume very high power. Okay. Otherwise, again the circuit conditions will be altered. Okay. Construction we have seen. That you have a moving system, you have a control system. Of course, the damping system and all are very specific to the instrument kind that we are using. So, we will discuss in the lectures where we will talk about PMMC or moving iron or dynamometer and how they can be actually converted into ammeter or how they can be converted into a voltmeter. Okay. Let us try to understand that how a simple galvanometer can be converted into a ammeter or a voltmeter, that we will see maybe in the next lecture, but right now let us try to understand that how a simple galvanometer can be converted into an ammeter. So, ammeter can be made from a low resistance galvanometer, which is basically designed to measure the current value. Shunt resistance, which is a low resistance wire, is connected in parallel with a galvanometer. So, this is a typical galvanometer structure, and this is the shunt resistance I am talking about. Okay. So, this is in the case of ammeter, a low resistance wire which is connected in parallel with the galvanometer setup. Okay. The shunt allows most of the current to bypass the galvanometer, which will protect it from very high current flow. Okay. Now, this arrangement extends the measuring range of the galvanometer, enabling it to function basically as a ammeter. Okay. We will see in more detail when we will talk about PMMC tool and others, that how they can be converted into ammeter or voltmeter. Of course, we have to also discuss the galvanometer, maybe we will take that after this discussion of voltmeter and ohm meter. Okay. So, as the galvanometer, this is again a construction of a simple ammeter which is based on this conversion of galvanometer. You have a rectangular coil wound on a light aluminum copper frame which is placed between the poles of a permanent magnet like any other PMMC tool. Okay. Now, when current passes through the coil, it experiences a deflecting torque. Okay. And this deflecting torque is proportional to the current value, and this is the gist of any kind of tool that we are going to discuss. Okay. Now, a low value resistance is connected in parallel with the galvanometer coil, which allow most of the current to bypass, as we have just seen, by protecting it and extending the basically the measurement range. Okay. Now, because the shunt resistance is very small, the total resistance of the galvanometer and the shunt is much smaller than that of only galvanometer. Okay. And this is very important for conversion of this galvanometer into ammeter. Okay. As we know that ideal ammeter is designed to have zero resistance, ensuring it does not affect the current in the circuit when connected in series. Okay. The pointer and scale of this ammeter is also very simple. The pointer is attached to the moving coil and moves over a calibrated scale which is marked in amperes, okay, or milliampere or microampere depending on what kind of instrument it is. And please note that this doesn't has to be linear always. It can be linear, it can be non-linear depending on what kind of tool I am utilizing, okay. And the deflection of pointer indicate basically the magnitude of current which is flowing in the circuit, okay. The control system and damping is mostly provided by small springs where the here springs provide the restoring torque, which is basically the part of control system which brings the pointer back to 0 when there is no current. And damping mechanism can be any, it can be by air or by eddy current depending on the instrument, okay, which ensure the pointer moves smoothly without any kind of oscillation, okay. In the DC circuit, basically you can use it, you can also use it in the AC circuit, but the value that they show are little different, okay. So the current remains constant in the DC setup, and the actual value is basically what you have for average value or say the RMS value. So you do not have different values for this, okay. So the ammeter shows basically the true value which is based on Ohm's law, okay. The ammeter shows the RMS value of the current, not instantaneous current for the AC circuits, okay. Like for example, for a sinusoidal wave which is having the kind of this equation I equal to I sin omega t, RMS value can be defined like this, and the RMS value for this sine wave can be given as I max by root 2, all of us knows, okay. Now this value is what is shown by the ammeter on your scale, okay. The heat produced by current in a resistor is given as I square RT, where this I is the RMS value and it is the effective DC value of an AC current because it produces the same heating effect in the resistor, okay. And say I max is for example 10 amp. For the same thing, if I calculate it the RMS value for the AC signal, I will have 10 by root 2 which is 7.07 angstrom. So a DC current of this particular value 7.07 amp gives the same heating effect as the AC current with 10 amp peak or say 7.07 amp RMS, okay. These things are very crucial to understand the basic ammeter configuration. However, this is just a basic overview of ammeter, and of course we will discuss about all the analog tools in detail, okay, and we will see that how they can be basically converted into ammeter or how the same instrument can be utilized as a voltmeter, okay. However, this basic configuration like how they are being connected, how a galvanometer can be converted to a ammeter, okay. Similarly, what is the concept of RMS current or DC current, these concepts are very much essential to understand those things. So we may not be discussing the same thing again and again. So I will request that you please go through this lecture very carefully while moving to the week 4 lectures. Thank you.